system. The joint work with Mukul Gazrani and Ashutosh Nair at USC, and Yi Oyang, who's at Berkeley now and probably is here somewhere. By system, I'm going to mean two specific models, Markov decision processes and a linear system model. And to some of you, this might sort of, remind about reinforcement learning. To others, it might mean stochastic adaptive control. So it, of course, has connections to both. But the perspective is a little bit different or fresh. We take an online learning perspective of the problem. OK, so I'm going to start with just a quick overview of MDPs and dynamic programming. And then I'll talk about Bandit models and online learning. And then I'll talk about reinforcement learning algorithm for unknown MDPs based on posterior, what's called posterior sampling. And then we'll see a similar algorithm for unknown linear stochastic systems. OK, so let me jump right in. So I'm going to assume that we have a MDP with over a finite state space. The action space is also finite. And so if you are in state X and you take action U, then you make a transition to the next state Y according to some transition probability theta. And then we get a reward, which is a function of the current state and the action. And of course, the controller gets to see both the state and the reward. And what we care about is the expectation of the long-term average of the reward, right? And we would like to optimize that. And so we're going to restrict our discussion to what are called weakly communicating MDPs, just to make sure that we guaranteed existence of optimal cost and optimal policy. And of course, we know that the optimal value function satisfies this Bellman equation, which is a fixed point in the optimal cost and the relative value function. And of course, there are many algorithms known for finding a solution to this fixed point problem. In particular, relative value iteration algorithm is one particular way you could find a solution. So the question is, what can we do when the MDP or the model is unknown? Specifically, the transition probabilities are unknown. And what one could try to do is one could try to do system identification, and then based on that, find the optimal controller. But in many applications, we don't have that luxury. We must learn and control at the same time. And the question is, OK, so in that case, what can we do? Sometimes we can learn or estimate the parameters and then come up with the control policy, and then based from that control policy, we get a control action, et cetera. When we can do that without losing optimality, we say that in adaptive control, we say that certainty equivalence holds, right? But it's well known that many times it doesn't hold, right? And the question is, in that case, what can be done? And specifically, the objective here is to find a learning policy that is optimal in the sense that it has the fastest possible learning rate or fastest possible rate of converging to the optimal policy. Okay, so that's the specific objective. And of course, that's the goal of reinforcement learning and one of the goals of stochastic adaptive control. And in fact, Borker and, one of the earliest formulations of this was actually given in Borker and Vara in the early 80s. OK, so one of the issues that arises why certainty equivalence doesn't hold is that you may not be doing enough exploration. So the learning policy has to kind of trade off exploration and exploitation to be able to kind of achieve this objective, right? And of course, that it's what it means is that it's an online learning problem, and immediately that should remind you of Bandit models. So let me kind of just talk about Bandit models. So just a very quick overview of a very, very basic setting. So let's say that we have two coins with unknown biases, and we're told to play this game. We can play this game, let's say, 100 times. Each time, we can choose either coin, and we toss it. And if it comes up heads, we get a reward of $1. Otherwise, we get 0. And we like to maximize our payoff. So kind of that tells you that it's not enough to say, well, for first 50 times, we can toss this coin and then get an estimate of the bias θ1. And then next 50 times, we can toss this coin and get a estimate of the bias θ2. That's not enough, right? Because that may not be the optimal strategy. So we'd like to, as I was saying, we'd like to maximize the expected long-term total reward. And sort of another way to kind of ask the same question is in terms of regret. So we define a notion of regret. So the first term here is the so if you knew which of the two coins is better, meaning has a higher bias of heads, then this would be the expected reward that you would get by just playing that coin, right? And then the second would be this is the expectation of the total reward that you would get for under some learning policy fee, right? And the difference of the two is the regret, right? So the question of, what is the policy that will maximize the expected long-term total reward is equivalent to sort of minimizing the expected regret, okay? Now this at least problem as stated was given by Lai and Robbins in the mid-'80s, and they also gave a lower bound on any learning policy, and they showed that there is no learning policy that can achieve regret better than log t. So it cannot grow slower than log t. Or in other words, convergence to the optimum cannot happen faster than log t by t. Okay, that's the best that can happen. And by now, of course, today morning you heard about the UCB algorithm, and probably maybe everybody here knows about the UCB algorithm. So UCB algorithm is one algorithm that can actually achieve this lower bound as well. So in that sense, it's order optimal. And the way it works is that you define an index for each coin or each arm, and it looks the following. So the first term here is just the average reward that you got from tossing coin I. And the second term is, you can think of it as accounting for the variance in your estimate, but it is, or standard deviation in your estimate, but it's really not that. It is, there is, so it is somehow, controlling how your exploration for the various arms. And the algorithm is very simple. So at each instant, you pick the arm or the coin that has the highest index value, okay? And so very rough intuition for this is that this is sort of an upper confidence bound on your estimate of the unknown parameter. And at every instant, you should pick the coin that has the highest upper confidence bound, which is independent of what the distribution is like. So in that sense, it is sort of taking an optimistic decision. So this is an example of class of learning policies that are called optimism in the face of uncertainty. Okay. So what happens with this kind of algorithm is that somehow this is able to trade off exploitation and exploration. So to kind of do that, you need some randomization, and so it so happens that an index policy like this is able to achieve that, and it is able to achieve that in an optimal way.
Can you just go through the policy? And what is TT? Just what is
that? Oh, sorry. So this is just the sample average from tossing coin I. Ti is the number of times up to time t that you have picked coin I. So what happens is that when you pick coin I, this is going to go down because Ti is going to increase, right? If you don't choose I, then this index value increases as square root log t. Okay? So it's not strictly speaking upper confidence bound because it is increasing. I mean, as you have more samples, you would expect the upper confidence bound to decrease, but that's not really happening. There is this inflation factor in this index. Okay? So it's a proxy for upper confidence bound. Okay? So the point is that that this algorithm is able to kind of do some randomization, and it trades off exploration and exploitation, which is optimal, at least in the which is order optimal. Now the other thing that happens with this is that if you look at what the algorithm does is that it does exploration that gets spaced exponentially apart. Okay, and that's the reason why regret grows as log t. Okay, but turns out this is not the only way that we can solve a problem like this. So here is another way. So here what you do is you maintain a posterior distribution over the unknown parameters, and then you sample from the posterior distribution, and then you just pick the coin that gives the highest sample, right? So very simple, intuitive, natural algorithm. And indeed, it was, back in the 1930s when Thompson was thinking of a similar problem, this is what he proposed to do, of course, with no proof. And so it so happened that this was lost, and then in 2011, a couple of guys in Yahoo Research, they rediscovered this algorithm, and they found that numerically it performs even better than UCB type algorithms. And then a year later, there was a proof of regret for this algorithm, and it turns out that regret grows as log t for this algorithm as well. Okay, so now as I was saying, it's a very simple natural idea, right? But what's really happening here is that you're really doing randomization based on posterior sampling, and it's happening in a way that it is able to kind of, trade off exploration and exploitation in an optimal manner, right? So another alternative to kind of for the multi-unbounded problem. Now the other thing that's happening here is that it may not be apparent when you look at the simple two-unbounded problem, but when you try to generalize UCB type algorithms, you have to do a lot of computation. So you have to, every instant of time, you have to solve an optimization problem. But here, there is no optimization problem that you're solving. So all you're doing is you're just doing sampling. So computationally, it is better. It has superior numerical performance, and it is computationally simpler. OK, so now after all this, now let's go revisit the problem that I had set out with, which is to find a learning policy for an unknown MDP. And the learning policy, of course, is going to be a function of the entire history that you see up to time t. And we would like this learning policy to search over some parameter space theta. Okay? And specifically, the objective of learning is to minimize the rate of growth of regret. Okay? So this is just a counterpart of regret that we saw earlier. Now, one lower bound that is known for this is square root t. So as opposed to the finite on Bandit problem, where the lower bound is log t, here you cannot achieve log t. You can at best get a square root t. OK, so now I guess I have motivated why we should consider posterior sampling based learning policy for this problem. Specifically, it's computationally simpler. So now let's see how one can do that. So it's the idea behind the algorithm is very, very natural. So you divide time into episodes, and these episodes have dynamic. The length changes dynamically, and then so at the beginning of the episode, you're maintaining a posterior over the unknown parameters. You sample from those parameters, and then you pretend that those are the true parameters. You compute a policy, and then you use that policy for the rest of the episode. Okay, so that's the policy. So at the beginning of the episode, you explore, then you exploit, and then you resample, then you compute a policy again, then you exploit again, et cetera, et cetera. Okay, so very natural algorithm. The only thing we need to worry about is how should we adjust the length of the episode, right? Or in other words, what should the exploration schedule be? That's the thing we need to worry about. So turns out that there are two things that determine what the length of the episode will be. One is that the episode is increasing. We increase the episode by 1 every time. Okay, and I'll revisit this why we are doing this by increasing by 1 every time. So at every time instant, so t2 is going to be t1 plus 1. Okay, so it cannot be larger than that. But sometimes this doesn't work. So we also need to keep track of the following: that we keep track of the number of visits through each state action pair, and if at any time instant t, the number of visits to state action pair xu is greater than twice the number of visits to xu at the beginning of the episode, then it means that this current policy is not doing enough exploration. So you need to end this episode, you need to resample, compute a new policy, and then begin all over again. Make sense? Okay. So like I said, this is the only thing you need to design. Everything else is sort of apparent. This is a natural way to design the rest of the algorithm. And then the other thing is that every time instant, you're updating the posterior using Bayes rule. That's it. Okay. So there's no optimization. It's just, well, okay. So there is of course, devil is in the details. So one thing is that you have to compute the policy at the beginning of the episode. You can use it. You can do that using your favorite dynamic programming algorithm. Okay. Unfortunately, there is no way around it. You can do that approximately, or you can do that exactly, but there's no way around it. Okay. All right. Okay. So what we can show is that for this algorithm, the regret.
Can you explain the
So you resample the parameters. So parameter theta is just the transition probability of the MDP. And then you solve a dynamic programming problem. You can use value iteration or policy iteration.
Use that policy from that.
Yeah, and then you get policy pi star, which would correspond to if the true parameter was theta, right? And then you just continue for the rest of the episode.
What prior do you use on theta?
So that's a very good question. So in principle, you can, presuming that you have some knowledge already, some information already, so you can use that prior. But in practice, what happens is that you use some nice prior, like a Gaussian prior or something, or beta prior, so that the computation in the updating the posterior is easy. So that's what is typically done. Okay, so what we can show is that the regret is upper bounded by square root t up to a logarithmic factor. And this is non-asymptotic, and all the constants and everything is known. Okay, so the other thing to note here is that actually it does scale sort of linearly. The upper bound scales linearly in the state space size, and it's square root in the action space size. And like I was said that the algorithm works even you can use approximately optimal policies, and this algorithm will still work. Now, why can the episode length increase more than one each time? That's not an artifact of the proof. In fact, empirically, we found that you can't do more than that. Now, is there another algorithm that that can have sort of a better schedule? We don't know, but we tried other schedules, and it turns out that by increase the episode length by one or by some constant is the best you can do. You can't increase it. For example, in UCB algorithm, you can increase the exploration time between explorations exponentially. You can actually have a deterministic schedule, and it'll still work. But that doesn't happen here. I think it seems to be sort of, that for this problem, you can't do that. Okay, so just to give you a sense of whether it works or not numerically, so this is tested on some benchmark problem called reverse swim. And this corresponds to an algorithm called UCRL2, and at least it seems that the regret is growing sublinearly, which means that if you look at per unit regret, you are going to have convergence. But for this algorithm, which is lazy PSRL, the regret is going linearly, and you may not even get convergence to the optimal policy. And then there is another algorithm, TSMDP, where you need to specify a recurrent state. So if you specify a good recurrent state, it turns out that it performs quite well, but otherwise it doesn't. Okay, so that's, as far as we know, it's the state of the art. Now, of course, there is the earlier, literature in stochastic adaptive control, but those give asymptotic guarantees. Okay, just a quick word about proof. The key. There is a lot of levers you need to crank, but it's mostly straightforward. The key is that you need to ensure that this property, that for the algorithm, that expectation of any function of the parameter theta k and a random variable x, which is adaptive to the filtration generated by the history, that's equal to the expectation of the function of the true parameter and the same random variable. So this is what you need to check when you're designing the algorithm. Everything else is housekeeping.
So I have a philosophical question.
Yeah.
So in most of the reinforcement learning literature, they parameterize the value function. So it's approximated by a neural network or some linear basis functions or something. Like here you're parameterizing the probability transition matrix. So can you say something about when one is better or worse? Or
So reinforcement, so the way I understand it, reinforcement learning is about two problems. One is sort of the dynamic programming part, if you will, right? Which is what you're referring to. So, if you have large state space or continuous state space, then you have to do function approximation, and you can either do that with value functions on the policy space, et cetera. But the other is the exploration, and it's sort of how should you explore? So usually there is no prescription for that, right? That's more or less an open problem. So this is a prescription for how should you explore. Now you can, so you are computing, so at the beginning of every episode, you are computing a policy. You can compute that policy using exact value iteration or policy iteration, or you can use any kind of function approximation neural networks. So yeah, so that's somewhat an orthogonal issue to this.
But it relies on the fact that there's a parameterization of the probability transition matrix.
Oh, but that is right. I mean, for this model, it's not a problem. When you have finite state space and finite action space, it's there are a finite number of parameters that you need to worry about. That completely specifies the model. So that's not an issue.
Well, probability transition matrix could be anything, right? Why is that parameter?
No, but the number of parameters is finite.
I think the dimensionality is the parameterization by value function would be R to the number of states, whereas with these IJU it would be state square times control. So it would be a much higher dimension parameterization with theta.
Right.
It would be higher dimension parameterization than this parameterizing value function.
This is there is no assumption. So this is fully parameterized in the sense that, right? So I mean, these thetas live in some product of probability simplexes, right?
And the state space, then the probability transition matrix is n by n, so you need n square parameters at least, and then there's control also on top of that.
That's right. That's right. Yeah, that's the. Yeah. Okay. All right. Okay. So. So sort of the main conclusion from here, this is that these kind of posterior sampling based algorithms, somehow they are able to do randomization such that in a sort of that you can learn at the optimal rate, if you will, right? The question is whether that this can go beyond just this model, right, or not. Okay, so for that, do I have 5 minutes? Okay, so for that, let's look at a stochastic linear system with unknown parameters. So it's the standard model, and then the parameters A and B are unknown, and we're going to consider quadratic cost, but that's really just for the reasons of tractability, because for that's the model for which we can compute something, right? And again, the objective is a regret. So we switched from considering reward to cost, but everything is more or less the same. And of course, for this model, we know that there is an optimal control policy, which is linear. So you just get a solution of the Ricardi equation, and then that gives you the gain, and then you have a linear policy. Optimal policy. Okay. So one assumption we are going to make is that in the parameter set, for every theta, there is a unique positive definite solution to the Ricardi equation. Otherwise, we can't do any computation. So, right? Okay. All right. So, just a quick word about sort of adaptive control. So, of course, this is not a new problem. The key idea at least in most of adaptive control, classical adaptive control, is certainty equivalence, and also it is well understood that it doesn't always work. There are counterexamples, right? And that is why I think the cost bias maximum likelihood approach was introduced by Kampi and Kumar for the same problem, and it asymptotically converges to the optimal policy. Recently, people have been worrying about non-asymptotic performance, and so there is few algorithms, but these are of the flavor of optimism in the face of uncertainty. So you can think of these as generalizations of the UCB idea, but they have to do a lot of computation. So every time instant, when you need to recompute a policy, you have to do solve a optimization problem. Okay, and yeah, that's what it is. So how would one construct a posterior sampling algorithm for this? So it's exactly the same idea. You divide time into episodes which have dynamic length, and the length of the episode increases by 1 each time, unless you're not doing enough exploration. And the way we keep track of not doing enough exploration is you are getting an estimate of the parameter and its covariance. So if the covariance becomes half of, or the determinant of the covariance is half of what it was at the beginning of the episode, it means you are not doing enough exploration. It's better to just resample, recompute, and start all over again, so to speak. Okay, so yeah, so that's the algorithm, and so this is and it works in the sense that. So this is showing per unit regret with the number of iterations. There are 2 plots here. You can ignore that. I mean, that's sort of an artifact of the simulation. But basically, you see that for an open loop stable system, the per unit regret is, well, it's decreasing. I mean, and I think at least the theorem implies that it converges to 0. One can't conclude that from the plot. And even if the open loop system is unstable, you see that the per unit regret decreases and seems to converge to 0. In fact, you can prove that the expected regret is bounded by square root t up to a logarithmic factor. Now, one thing that is, we do have to assume that the algorithm will keep the system closed loop stable. Okay, so this is an artifact of the proof. Unfortunately, we have not been able to get rid of this as of now, but in the simulations, it never seems to come into play. Okay, so all right. With that, so I introduced posterior sampling-based learning to control algorithms for MDPs and linear stochastic systems. And as I mentioned, so initially I was a little bit skeptical about this, but it seems to sort of, it's a very does exploration versus exploitation in a very structured way, meaning that it's doing randomization, but it's a very systematic way of kind of design. It's well known in adaptive control that you can add randomization, and then you can get around the problem that certainty equivalence doesn't hold, right? So this is sort of a very systematic way of doing that, right? And the results in a very natural design. In some other class of problems, we have seen that you can design a deterministic schedule of exploration, and that works specifically for finite on bandit problems. We don't know if we can do that here. As of now, I believe it should be possible, but as of now, we couldn't do that. And now, another issue which is kind of what was asked was, can this be combined with can this be extended to continuous state space MDPs? So we don't have that yet. So I believe that it is an orthogonal issue. So you could do function approximation in finding the optimal policy at the beginning of every episode, and it should be possible to kind of extend this. And I believe there is a potential to kind of address, sort of learning for time-varying systems as well, where let's say the parameter is varying according to a Markov chain or something like that. But again, we don't have that yet. All right, so with that, I'll stop here. So thank you.
Questions?
Yeah.
What was the dependence on the prior reference?
Oh. Dependence on the prior. So that's a very good question. So that's buried in the expectation. So it's expectation of the regret upper bounded by something. So the expectation is with respect to that prior. It's base regret, yeah. But the upper bound is independent of that.
So for the continuous setting, have you looked into the case with LQG but unknown coefficient matrix?
Not sure I understand. So
I will have a linear dynamic system, but
yeah.
coefficient matrix. So xt plus 1 equal to a multiplied by xt and b multiplied by ut. But this a and b are unknown to you, and you want to learn that. have you
That's what we're doing, right? A and B are unknown.
That's in the state, and, control matrix. He's talking about the cost function.
Oh, cost function, Q and R. In the cost, no, we have not. I don't know. Probably it should not. I mean, it should be possible to do it, but I don't know. Yeah. Yeah. That should not be that shouldn't be difficult. In any case, see, you probably only need a finite number of samples to actually infer Q and R, and after that you know it, right? Because you get to see the cost, the per stage cost exactly, and even if you don't know Q and R, you know X, you know U. So from some samples you can compute that. The more, sorry.
The rest of the questions offline and go to break. We'll resume promptly at 3:45.